Okay, fine. So let me share the screen. Yeah, screen is visible.
Yes.
Visible, right? Fine. So yeah, we are doing what we have started. We have started this alkyl lithium compounds. Okay, alkyl lithium compounds. So suppose you have this question or this example. So here I have this bromobenzene. Okay, bromobenzene. Now number one reagent is this butyl lithium. Okay, and what is number two? Number two is this CO2 in presence of H plus. So what will happen? So what is the starting material we have? The starting material here we have bromobenzene, and now we are treating with butyl lithium, right? So again what will happen here?
Metal halogen exchange.
Metal halogen exchange. So basically butyl minus, this is what, lithium plus. Now butyl minus will abstract the bromine. Okay, and what you will get? You will get this phenyl lithium. Okay, next step what you have? You have CO2. So CO2 means what? You have this carbon double bond O, double bond O. This lithium is actually positive and this phenyl ring is actually negative. So this negative charge will attack on the carbonyl carbon. This bond will break. So ultimately what we are getting? We are getting what? Carbon double bond O, and this is becoming what? O minus. Now next you have H plus. So basically H plus will come and it will attach with your O minus. So okay, after all it will be protonated. So after all what we are getting? We are getting OH. Okay, benzoic acid. Clear? Done?
Yes, sir.
Done? All of you done, right? Fine.
Sure.
Okay. Next, suppose you have this carboxylic acid, RC double bond OH. Okay, so you have carboxylic acid. Now we are using excess butyl lithium. Excess butyl lithium. So what will happen?
Acid base reaction.
Acid base reaction. So again butyl is minus, lithium is plus, and see here you have acidic proton. So when you have acidic proton, butyl minus will takes up the proton. Okay, and what we are getting? We are getting R C double bond O minus. Okay, this thing I am getting. Lithium plus is the counter cation part. Okay, now again you have butyl minus. Okay, again you have butyl minus because we are using in excess. Okay, so butyl minus will attack on the carbonyl carbon, and again this bond will break. So what I am getting? I am getting this RC. Here you have butyl group. Here I am getting O minus. Here also you are getting O minus. Okay, if you do workup, okay, can you switch off your mic? I think, yeah, otherwise in recording also the background noise will come. Okay, fine. So this thing we are getting. So after workup or H3O plus, what you will get? You will get OH. Okay, and I told you guys that when one carbon atom has two OH group, what will release? Water will release from here. Okay, so water is releasing from here minus water, and what I will get? Ultimately we are getting this ketone compound. Okay, so if you use excess of butyl lithium, that time you will get this ketone compound from the carboxylic acid molecule. Clear? Done. Write it down if you have it out. Write it down. Done. Okay. Okay, fine. Now next, suppose you have this molecule. This molecule. So here I am using butyl lithium. What will happen? Ortholithiation, correct. Ortholithiation. So ortholithiation means what will happen? Chelation will happen. So again, oxygen has lone pair. Oxygen will donate the lone pair to lithium plus. Okay, and here you have butyl minus, and this is the proton. So butyl minus will takes up this proton, and the lithium, you have to introduce the lithium. Which position? Ortho to your this OCH3 group. So lithium will introduce here ortho with respect to OCH3. Okay, similarly if I use, suppose you have same compound and now you are using butyl lithium in presence of tameda, that time what you will get? Butyl lithium in presence of tameda, that time what will happen?
Next to fluorine it will abstract.
So that time tameda is basically, tameda means what? Tetramethyl ethylene diamine, this structure, right? This structure. So tameda now will chelate the lithium plus. Okay, tameda will chelate the lithium plus. Okay, and butyl minus is free. When tameda chelating this lithium plus, so that time butyl minus is totally free, and when it is free, so that time it will abstract the most acidic proton. So as fluorine is most electronegative in the periodic table, or I can say it is more electronegative than oxygen, that's why this proton is more acidic. Okay, so that's why now the lithium group will introduce here ortho position to your fluorine, ortho position with respect to fluorine. Clear?
Yes, sir.
Okay, write it down, then we are done. Done, right? Okay. Now suppose you have this. So here you have one methoxy group and here you have one methyl group. Okay, now same thing, we are using butyl lithium. So what will happen? Ortholithiation. From which side it will abstract the proton? Right side or left side? Ortholithiation will happen, but which side it will take up? Which proton it will take up? This proton or this proton? That is the question here.
Right side, sir.
Right side. So see, here you have, here why the proton is abstracting from here, because both are electron withdrawing group. Okay, both are electron withdrawing group. But if you see here this methyl is basically electron donating group, right? So it has plus I effect as well as you have plus H effect. So if it abstracts this proton, suppose it is abstracting this proton, so what you are getting? So you have here methoxy group, here you have methyl group, and the negative charge is forming here. Okay, so this carbon ion is basically unstable. Okay, this carbon ion is becoming unstable. Why? Because you have electron donating group here. In the previous example, both the groups are electron withdrawing. Here, this is electron donating. One is electron withdrawing, this one minus I, but methyl group will show plus I or plus H. Okay, so that's why it becomes unstable, and that's why the butyl minus will abstract the proton from the left hand side. So what you will get? You will get this thing. Okay, lithium will introduce this position, this left side. Okay, lithium will introduce in the left side of the methoxy group. Fine. Now suppose you have the same molecule. Okay, same molecule I have. OCH3 is there, CH3 is there. Now here I am using this butyl lithium. Okay, in presence of what? In presence of tamida. In presence of tamida, that time what will happen? So tamida basically what? This tamida chelates the lithium plus, right? It will do chelation with the lithium plus. Okay, you guys write down here, you guys write down, this is what? This is your ortholithiation. So write down the things, otherwise you will forget. Ortholithiation. This is not ortholithiation. Here tamida will chelate the lithium plus, so butyl minus will be free now. So it will abstract the most acidic proton. Now which one is most acidic proton? Definitely it's not. Okay, this right hand side is not acidic. So which side proton will be most acidic? Left side already, that is your ortholithiation, na? If you abstract the proton from left side, so that is your ortholithiation, that is not your most acidic proton. So in this particular example, it will abstract the proton from this methyl. Okay, now why it is most acidic? So suppose you have CH2 hydrogen, so butyl minus is abstracting the proton from this methyl group. Now why it is most acidic? Let's see. So you have your benzene ring, here you have OCH3, okay, and what I have here? Here I have CH2 minus, right? Now you can see this CH2 minus basically is in conjugation with the benzene ring, so it gets stability. Okay, it is very stable carbon ion, and that's why this proton is actually most acidic proton. Okay, clear? So what you will get? You will get this kind of thing, CH2Li. In presence of tamida, you will get this. But if you have, if tamida is not present, that time ortholithiation will take place and you will get that product. Okay, not this. This is one is unstable. This product you will get. Clear?
Yes, sir.
Yes, sir.
Clear, right? Fine. So next we have, write down next, catalytic. This is the next topic. Okay, alkyl lithium we have finished. So this is what? Catalytic reduction. Catalytic reduction. Okay, so first of all, write down some reagents here in catalytic reduction. What do we have? Hydrogen, platinum. Okay, we have hydrogen, palladium in presence of carbon. You can have hydrogen in presence of Raney nickel. Okay, Raney nickel. You can have hydrogen in presence of PtO2. PtO2 means what? Platinum dioxide, right? And together this reagent, hydrogen PtO2, this is together known as what? Adams catalyst. Okay, Adams catalyst. Clear? So these are the type of reagents we will use here, catalytic reduction. Okay, apart from that, we have a very popular reagent that all of you know, I guess, what?
Lindlar's catalyst.
Lindlar's catalyst. Okay, so Lindlar catalyst, what will happen? Alkyne will convert to what? Cis alkene. What is Lindlar's catalyst? So hydrogen in presence of what? Palladium, calcium carbonate, okay, lead acetate, okay, lead acetate, or you can use quinoline. Okay, so this is basically your Lindlar's catalyst. Hydrogen, palladium in presence of calcium carbonate, and the solvent can be your lead acetate or quinoline. Okay, now this whole catalytic reduction are of two types. Okay, we have two types here, two categories we have. So one thing is known as your hydrogenation. Okay, hydrogenation, and the second thing also known as hydrogenolysis. So these two things are totally different. Okay, hydrogenolysis, one is what? Hydrogenation, and another is your hydrogenolysis. Okay, so what is hydrogenation? So hydrogenation means addition of hydrogen. Okay, see here you have ION, here also you have ION. So hydrogenation means always what? Addition of hydrogen. And if you add hydrogen, what will happen? The alkene, or suppose you have alkyne, okay, alkyne, those compounds will converted actually into alkane compounds. Okay, if I talk about hydrogenolysis, so that time what will happen? That time write down cleavage of bonds. Okay, cleavage of bonds. Okay, bond cleaving will take place. Fine. So these are the two things we have. One is hydrogenation and another is your hydrogenolysis. Hydrogenation means what? Addition of hydrogen. So whatever you have, alkene or alkyne, unsaturated compounds will convert into saturated. Okay, and if you have hydrogenolysis, so there what you will get? Cleavage of bonds will take place there. Fine. Now suppose I have this kind of compound. Okay, suppose this is your benzene ring, and here you have CH2OH. Okay, if you use this kind of particular reagent, so what will happen? Always remember this benzylic bond. Benzylic means what? Benzylic means this kind of bond, PHCH2. Okay, so that can easily cleave. Okay, this is not about carbon oxygen bond, this is about your benzylic bond. So if you have benzylic, okay, that can easily cleave. Okay, and if you have heteroatom bond, suppose you have this is a Norborane type of system. Okay, Norborane type of system you have. If I use here Adams catalyst, or you can use hydrogen palladium carbon. Okay, so what will happen? This oxygen bond will cleave. Okay, and ultimately you will get this kind of product. This. Okay, so heteroatom bonds as well as this kind of benzylic bond will cleave out. Clear? This kind of heteroatom, this kind of hetero bond is actually very weak. Why they are weak? Why this bond is cleaving? Because due to what? Electron repulsion. Okay, due to electron repulsion, already this bond is very weak, that's why the bond is breaking. Okay, now I am giving one question. Suppose you have, this is not a question, this is your example. Suppose you have this kind of molecule. Okay, so this is a molecule. Here I am giving this reagent, hydrogen, okay, 10 percentage palladium carbon in presence of methanol. So methanol is the solvent here. You have this reagent, hydrogen, palladium carbon. Can you guess what will happen? Which bond will break here?
PHCH2, sir. PHCH2.
PHCH2, this is benzylic bond, right? So this benzylic bond will break first of all, okay, and if this bond breaks, check what you are getting. So you are getting here O minus, right? So O minus means what? This CO2 gas can release from here, right? Carbon dioxide gas can release from here. So this carbon nitrogen bond also can break. So what are the eliminating products you have? If you break this bond, what you will get? You will get this toluene. Okay, see, PHCH2 you are breaking, so that means hydrogenation means what? You add one hydrogen this side, one hydrogen this side. Okay, fine. So not to think like that, but basically, yeah, you will get this toluene product, and CO2 is releasing from here. Okay, because it's a when the gas is releasing, it becomes what? Thermodynamically favorable process. Okay, so it's a thermodynamically favorable process because carbon dioxide gas is releasing. And what is the left part you have? You have this amine part, NH2, and now you have this double bond O. Here you have NH, okay, this you have NH, and here you have this. Okay, so this part remains like same, nothing is changing here. What is cleaving, what is changing? The toluene group is releasing from here, as well as the carbon dioxide gas is releasing from here. Okay, so that is the example of your hydrogenolysis. Clear?
Yes, sir.
Yes, sir.
Clear, right? Okay, who's are present here? Fine. Okay, now next, write down here, this side write down functional group. Okay, functional group, and this right side write down reduction product. Reduction product. Okay, so suppose you have functional group, we are doing hydrogenolysis or hydrogenation we will do. Okay, we will do hydrogenation. So suppose you have acid chloride. Okay, acid chloride. So what will happen? Hydrogenation. Okay, you have to do what? Hydrogenation. So what will happen? Attach one hydrogen this side, one hydrogen this side. So what you will get? You will get aldehyde. Okay, HCl is the byproduct, no need to write down the HCl. Okay, now suppose you are doing further hydrogenation of this aldehyde, so that time what you will get? Now attach one hydrogen here with carbon and one hydrogen with oxygen. So what you will get? You will get RCH2OH, alcohol. So if you do hydrogenation of acid chloride, what are the products you will get? You will get aldehyde as well as what? As well as alcohol. Aldehyde and alcohol you will get. Clear?
Yes, sir.
Number 2, write down if you have nitro group. Okay, nitro group. So this is very simple, you already know. Nitro, when it will reduce, it will produce what? Amine. Okay, if we do reduction of nitro functional group, we will get amine compound. Okay, number 3, suppose you have triple bond. So RC triple bond CR dash. Okay, so based on the reagent you will get cis alkene, trans alkene, but here I am writing in general. Okay, So I am not mentioning any cis trans. So basically you will get like this carbon carbon double bond, and if you do further hydrogenation of that, okay, so that time you will get simply alkane. So R CH2 CH2 R dash, okay, and this alkene you will get based on the reagent what you are providing, okay. Number 4, suppose you have this aldehyde RCHO. So what I will get if I do reduction of aldehyde, what I will get? I will get RCH2OH, alcohol. Fine. Suppose I have alkene compound RCH double bond CH bond R. So if I do reduction of that, what I will get? I will get RCH2 CH2R, alkane compound you will get, okay. And suppose number 6, you have this kind of ketone product, okay. So if I do reduction of ketone, what I will get? I will get secondary alcohol, and if you do further hydrogenation, that time you will get water plus this alkane, okay. Add one hydrogen this side, so you will get alkane plus water. Fine.
Okay, sir.
Done. Okay, now suppose number 7, I have this molecule, I have this, and here I have this CH2O1. This is ether basically, okay, ether compound. So if you do here reduction, what you will get? Hydrogenation. So basically you have to cleave the carbon oxygen bond, so attach one hydrogen this side, one hydrogen this side. So what you will get? You will get here toluene,
Toluene.
toluene plus what? Toluene plus alcohol. Toluene plus alcohol, okay. Number 8, suppose you have cyanide compound, this, okay. So if I do reduction of that, what I will get? I will get primary amine RCH2NH2, primary amine you will get, okay. Number 9, suppose you have this ester, okay, RC double bond OR dash, okay. So what you will get if I do reduction of ester or hydrogenation of ester? First of all, see, you have to cleave this carbon hydrogen bond. So basically attach one hydrogen here, one hydrogen here. So ultimately what you are getting? You are getting alcohol R dash OH plus what you are getting? You are getting aldehyde. Now aldehyde will not stop, okay. This ester will not stop in aldehyde. It will do further reduction, and ultimately you will get what? Alcohol. Okay, I already showed you here that aldehyde you are getting, but after some time you will get ultimately alcohol. So the same thing will happen here also. Initially you are getting aldehyde, but if you do hydrogenation, ultimately you will get alcohol compounds, okay. And number 10, suppose you have this RC double bond O, okay, this is amide derivative NHR dash. So if I do hydrogenation of that, ultimately what you will get? So here you will get R CH2 NHR dash, okay, hydrogenation. So this compound plus water will release, okay. So these are the functional groups we have, okay, 1 to 10, okay. And keep in mind, if we move in the upward direction, okay, if we move in the upward direction, so basically the reactivity will also increase. So write down here that reactivity in catalytic hydrogenation. Reactivity in catalytic hydrogenation is increasing in this direction. Fine. Doubt? Any doubt?
Yes, sir. Yes.
Any doubt? Any doubt? You can tell
Sir,
me.
can you explain the
Which one?
10th also, last one?
Last one. See, basically, if you take amide, so here don't do like this. Okay, here don't add hydrogen here. That is experimental things, na. So add two hydrogens here and two hydrogens here. Okay, so basically water will release from this part, and you are getting this amine compound from here, secondary amine. Okay.
Yes, sir.
Fine. Okay. So suppose you have this example. This, okay, and here I am using this reagent hydrogen, okay, PTO2 methanol. What is this reagent? What is the name of this reagent? Hydrogen platinum oxide methanol. What is the
Adams.
Adams catalyst?
Adam's
Okay.
catalyst.
So write down Adams catalyst. Okay, so if you have Adams catalyst, what will happen? So keep in mind, hydrogen will add, definitely hydrogen addition will take place. Definitely hydrogen addition will take place if you are giving hydrogen, so that means hydrogen addition will take place. But what is the main thing here? Syn addition will take place. Syn addition or cis addition, anything you can call. Syn addition or cis addition will take place. Syn addition of what? Syn addition of your hydrogen. So suppose hydrogen is coming from below the plane, that is I am doing by myself only. Okay, you can show above the plane also, no problem. But what you have to show, you have to show the two stereochemistry of the two hydrogens same, not different. Okay, so if hydrogen is coming from the below the plane, so that means this star automatically it will move to where? Above the plane. And here this long chain, this will also move to what? Above the plane. So this. Okay, if I show the hydrogen in above the plane, that time you have to show it in below the plane. Clear? So that is syn addition. So keep in mind, if you are using Adams catalyst, what it will do? It will do syn addition of hydrogen. Okay, syn addition of hydrogen. Done?
Yes, sir.
That's good.
Done, right? Fine. Now suppose you have this. Okay, we have this, and here I am using this hydrogen, okay, in presence of what? In presence of Raney nickel. Hydrogen in presence of Raney nickel, okay, and they have mentioned this temperature also, 50 degrees centigrade, 100 atmosphere pressure. 100 atmosphere pressure. Okay, so what will happen? So first of all, see what is Raney nickel. So write down, suppose you have nickel aluminum alloy. Alloy means, you know what is alloy? Alloy means mixture of metals, right? Mixture of metals in different composition, that is your alloys. So if you are taking nickel aluminum alloy and then you are treating this mixture with NaOH, okay, NaOH with a base, so that time you are getting Raney nickel. So that is the procedure to make Raney nickel in lab. Okay, you will not get what I can say, like nickel in hand. First of all, you have to make it. Okay, most of the organic reagents you have to make by yourself. Okay, so nickel aluminum alloy, and if you are treating it with NaOH, so you are getting nickel. And now this nickel have two two functions, or I can say two things it can do. Okay, so first of all, the first thing is hydrogenolysis. Hydrogenolysis of sulfur compounds. Okay, hydrogenolysis of sulfur compounds. Okay, and number two, reduction of aromatic rings. Okay, so these are the two things you have to keep in mind. One is what? One is your hydrogenolysis of sulfur compounds, and second is the reduction of your aromatic rings. So here, do you have any sulfur compounds here in this molecule? No, right? So what will happen?
Reduction of
Aromatic ring will get reduced. Okay, so after reduction, what you will get? You will get this. Okay, don't do reduction of ester group. Okay, don't do reduction of ester, only the aromatic ring will reduce. Okay, again I am saying this catalytic reduction part is very selective. Okay, here basically this part only few examples we have, but you have to remember all the things. Okay, this part is very
When do we need to reduce ester groups? When do we need to reduce ester groups?
When you want to reduce, for reduction of ester, you can use lithium aluminum hydride. Okay, lithium aluminum hydride you can use. Okay, so this catalytic reduction is very selective. Okay, fine. Suppose you have this compound, and here I am using nickel. So what will happen? So hydrogenolysis of sulfur compounds, right? So that means this carbon sulfur bond will break, and you will get this cyclopentane compound. Clear? Two things you have to remember. First one is your hydrogenolysis of sulfur compounds, and second thing is reduction of aromatic rings. Okay, reduction of aromatic rings. So don't worry, when we will practice questions, that time it will be clear. But this part, again I am saying, this part is very selective. Okay, done?
Sure, sir.
Done, right? Okay, so again write down catalytic reduction. Catalytic reduction. Now what are the factors basically we can use to get a better reactivity? Okay, so what are the factors? So first of all, write down one line that reactivity of a catalyst can be increased okay, reactivity of a catalyst can be increased, and if reactivity is increasing, so that means the selectivity decreased. Okay, selectivity decreased. They are inversely proportional to each other, reactivity and selectivity. So if reactivity is increasing, selectivity is decreasing. If reactivity is decreasing, so that means you are increasing your selectivity. Okay, now what are the factors? So basically you can increase the temperature. Okay, temperature increase, this is number one factor. Number two, you can increase the pressure as well, pressure increase. Okay, and number 3, amount of catalyst. Amount of catalyst, that also you can increase to get better reactivity. So if you increase the temperature, it will actually it will overcome the activation barrier, because if you increase the temperature, more number collision will happen. Okay, and when more number of collision is happening, the activation energy is also decreasing, right? So if you increase the temperature or if you increase the pressure, ultimately your reactivity will increase. Or the third factor is what? You can use more catalyst, more amount of catalyst. That also is a factor. Done?
Yes, sir.
Done, right? So suppose here I am using one equivalent of hydrogen in platinum oxide, PtO2. What will be the product?
Syn addition happens.
Scene addition. Okay, fine, scene addition, but which double bond? One equivalent we are using, na? You have two double bond here.
The one next to CH3.
Why?
Because I'm more electron rich.
More electron rich. So okay, see, so whenever you are doing this kind of hydrogen addition or hydrogenation reaction, first of all, suppose this is your metal surface. Okay, this is your metal surface. Now you are adding hydrogen on this metal surface, because in lab basically what you will do, first of all you will take the metals, okay, and then you are passing hydrogen gas or something. Okay, so what will happen, basically the hydrogen will absorb on the metal surface like this. Okay, so that is the mechanism. Initially you have hydrogen gas, hydrogen bond is there. Now after some time this bond will break, and then now they are attaching with the metal surface. So what will happen if you have a metal surface? So basically suppose metal surface and these hydrogens are coming to this side, okay, and this metal surface and these hydrogens are coming to this side also. So which one is more feasible?
Say,
Huh?
downwards.
Downside. Why? Because if you
Because it
have a
is,
metal
yeah.
surface, so that is already sterically crowded, right? So basically
Yes.
the less substituted double bond will be reduced. Okay, less substituted double bond will be reduced here. Not the most substituted one. This one is more substituted. Okay, why? Because 1 2 3, so this is tri substituted, and this is your what? This is actually your mono substituted. No, sorry, this is di substituted, right? 1 2 di substituted. So fine, so what will happen? So yeah, scene addition will take place, but the thing is, if you do scene addition here, that is nothing of an use. Okay, you can show the stereochemistry like this: below the plane one hydrogen, here also below the plane one hydrogen. Okay, but see, already this center is not chiral. Okay, this center is not chiral, so no need to show any kind of stereochemistry. You can just show like this. Okay, you can just show like this, same thing. Okay, so basically the less substituted double bond will be reduced, okay, in presence of this. What is this? This is your Adams catalyst. Okay, this is again what? This is your Adams catalyst. So scene addition will take place. Scene addition will definitely take place, but this center is not chiral at all. That's why we are not showing any stereochemistry here. You can show it simply like this. Fine. So you just write down one line here, that the ease of reduction of double bond ease of reduction of double bond decreases with increasing in substitution. So that means if your more substituted double bond you have, so that means that will not be reduced. Okay, less substituted double bond will be reduced. Okay, clear? So that is actually your selectivity. Okay, because one equivalent we are using, you have two double bonds, it is selectively reduced the what, less substituted double bond, not the more substituted. Fine. So that is basically chemoselectivity. Okay, done.
Yes, sir.
Any doubt, tell me.
If we use the excess of the catalyst.
Excess of catalyst we are doing. Excess of catalyst we will do now.
Yes.
Excess of catalyst, that time both will reduce. Okay. So suppose here I am not mentioning anything, hydrogen PTO2. Okay, hydrogen PTO2. That time what will happen? That time both the double bond will be reduced. Okay, both the double bond will be reduced, and if you can see here both are what? Both are basically your what? Di substituted. 1 2, here also you have 1 2. Both are di substituted, and that's why both the double bonds are reducing. We are not maintaining any equivalent also. Okay, so if you use excess, that time definitely both will be reduced. Okay, but in exam you have to check the options, whatever the options they are giving, according to that you have to move. Okay, option elimination you have to do. Fine, done.
Yes, sir.
Okay, so I have this. Okay, I am using this hydrogen in presence of palladium, carbon, methanol. Okay, so if you use this reagent, hydrogen in presence of what? Palladium, carbon, methanol, so what will happen? Hydrogenation will take place. So you have a double bond. If you add hydrogen, what you will get?
Yes.
Okay, the double bond will reduce into single bond. Hydrogenation is simply taking place. Okay, hydrogen, palladium, carbon, methanol, you will get this. Hydrogenation is taking place. Okay, but see now, if we change the metal, suppose you have hydrogen and now I am using platinum, solvent is same, methanol is the solvent. See, only what we are changing, we are only changing the metal, palladium, carbon, and here we are using platinum. So that time what will happen? That time the double bond is reduced. Okay, double bond will reduce, as well as this double bond, this ketone group will also reduce, and you will get alcohol. Okay, so here both are reducing. Think like that, you are adding 2 hydrogen here, and here also you are adding 1 hydrogen here, 1 hydrogen here. Okay, so that much selective they are. Okay, if you are using with palladium, so that time see, only the double bond is reducing, the ketone group is becoming intact. Okay, it is not reacting. But if you change the metal center, if you change the metal, here we are using palladium, now we changes it to what? Platinum. So if I change it to platinum, that time what happening? The double bond is reducing, as well as this carbonyl group is also reducing. Okay, so just write down one point, that if you have platinum, okay, if you have platinum, so write down more exhaustive reduction more exhaustive reduction than palladium. Okay, so you can think like that. Palladium is soft, platinum is hard. Okay, platinum will do more exhaustive reduction than palladium. Fine.
Sir.
Yes, sir.
Done.
Done, sir.
Okay. Okay. Suppose I have this. Here you have a double bond. Here you have CO2H, and here I am adding hydrogen in presence of PtO2, platinum oxide. So what will happen? Do it.
No.
Do it. What will happen here?
Syn addition, sir.
Syn addition, right? Syn addition will happen. This is Adams catalyst, right? So now the question is from which side they will approach. Which side? Syn addition is fine below the plane. Why?
Sir. Because most radically hindered.
Above the side you have already this group, right? You
Yes.
have already this bridging type of thing. So the hydrogens will approach from below the plane, correct? The hydrogen will approach from which side? From below the plane. So write down that cis addition of hydrogen atoms from less hindered sites. Okay, less hindered sites. Okay, so cis addition of hydrogen atoms from less hindered sites. Done? Understood? Already above the plane you have this group. Okay, this bridging type of unit is there in above the plane, so that's why the hydrogen is approaching from below the plane, because also metal is already associated with your hydrogen, right? Metal surface is present there, so that definitely will find the less sterically hindered site. Okay, done?
Yes, sir.
Sir.
Done, right? Any doubt you can ask me. So here I have hydrogen in presence of what? In presence of PtO2. What will happen? Hydrogen addition, right?
Ketone will convert it into secondary alcohol, sir.
Secondary alcohol, fine. Secondary alcohol. Now the question is from which side the hydrogen will approach? Axial side or equatorial side?
Equatorial.
Equatorial. Why? Why not axial?
1,3 diaxial
1,3
interaction.
diaxial interaction. Yeah, Kaveri, tell me.
No, sir.
1,3 diaxial interaction, right? So again
Yes,
the
sir.
same thing. Suppose you have metal surface here, and here you have hydrogen. So if the hydrogens are approaching from this side, so already you have here methyl, right? So they will do repulsion, 1,3 diaxial interaction. Okay, and if it is approaching from this side, this equatorial side, that time there is no repulsion. Okay, 1,3 diaxial interaction is not present here. Okay, so hydrogen will approach from equatorial position, OH will move to here, axial. Okay, that will be your major product. Okay, okay, here also seen addition, but the thing is it will attack from the less sterically hindered side. Fine, this one is your major product, and the minor product also you will get like this. Okay, I am showing you the minor product. So the minor product will be like this. Understood?
Yes, sir.
Any doubt? Any doubt?
No, sir.
No, right? Okay, so now write down that hydrogenation of substituted cyclic alkenes gives trans addition with palladium. Okay, so hydrogenation of substituted cyclic alkenes. Okay, substituted cyclic alkenes gives trans addition with palladium. Okay, so I am showing you. Suppose you have this statement, you have to remember. Okay, hydrogenation of substituted cyclic alkenes gives trans addition with palladium. So suppose I have this. Okay, again I am saying this catalytic hydrogenation is very selective topic. Here you have to remember. Okay, you can refer Carothar's book, there you will get these examples, you will get there also. Okay, 1 to 2 example is extra there, you can check that. Okay, if you are interested, otherwise you can follow the notes. Okay, so hydrogen, palladium, carbon, if you use this thing na, if you are using palladium and if you have this kind of, what I can say, cyclic double bond system, so that time you will get this. So this is one ring, this is one ring. So now the hydrogen addition will take place like this. One hydrogen will be above the plane and the other hydrogen will be below the plane. That is your trans addition, right? That is trans addition. You will get 79% of this product. Okay, and cis addition or syn addition will also take place. Okay, syn addition or cis addition will also take place, but that will be around 21%. So if you are using hydrogen, palladium, carbon, that time you will get trans addition of hydrogen. Clear?
Yes, sir.
Clear?
Yes.
Okay, so suppose you have this. So here I am using hydrogen in presence of palladium, and here I am using hydrogen in presence of what? Platinum oxide. Write down the products.
First one give trans products, the second one gives cis product.
First one will give you trans product. Okay, so definitely hydrogen addition will take place, but what? Trans addition, right? So suppose methyl is above the plane, so that time hydrogen will be below the plane, and here hydrogen will be above the plane and the methyl will be below the plane. So that is your trans addition, and that is actually your major product. Okay, I am not writing down the minor product. I think you can write down the minor product. Okay, minor product means what? Minor product you will get here syn addition. Okay, or cis product you will get. Cis one will be your minor. Okay, and if you are using Adams catalyst, that time what will happen? Which one will be major? Cis one will be your major. So that time both the methyl will be above the plane. Okay, and definitely if methyl is above the plane, so that means hydrogen is what? Hydrogen is below the plane. Okay, so that one will be major, and here the trans product will be your minor. Okay, clear? So Adams catalyst will do cis addition of hydrogen, and this hydrogen palladium will do trans addition of hydrogen. Clear?
Yes, sir.
Clear, right?
Yes, sir.
Fine. So suppose I have this CH3, okay, then I have this CH2 whole 7, okay, again you have this carbon carbon triple bond, here you have also CH2 whole 7, COOH. Okay, here I am using this reagent. Okay, so hydrogen, palladium, calcium carbonate, quinoline. What will be the product?
Cis alkene, sir.
Cis alkene. This is what? This is your
Yes, sir. Last.
Lindlar's catalyst. Correct. This is your Lindlar's catalyst. Apart from Lindlar's catalyst, you can also use diol H. What is diol H? What is diol H?
Reducing agents.
Reducing agent. What is the name? What is the name of diol H? Diisobutyl aluminium hydride. Okay, diisobutyl aluminium hydride. See, revise organic chemistry. Okay, I am again saying revise the organic chemistry part, otherwise you will forget all the things. And before exam time you cannot do anything. When you have only 1 month, that time you cannot do anything. Okay, so better to revise from today. Okay, just study at least 1 to 2 hours only organic. Okay, again I am saying organic chemistry is scoring. Okay, organic chemistry is very much scoring. I can say inorganic chemistry nowadays in NET exam, inorganic chemistry becomes pretty much unpredictable, but organic they are not making like this, because organic they cannot do like this. Okay, organic is linked to each and every chapter. Okay,
Yes, sir.
so this is what you are getting: cis alkene, hydrogen, palladium, calcium carbonate, Lindlar's catalyst, or you can use diol H. You will get your cis product. Okay, Kaveri, done? Understood? Any doubt?
This table, sir. Is this table, sir? Steric hindrance.
Steric hindrance is there. Steric hindrance is definitely there, but yeah, still it is stable. Okay, still it is stable. How it is stable? So you can show like this: carbon carbon double bond. You have hydrogen hydrogen. Now 7 CH2 na, so that will be like this. Okay, and this thing will be like this. Okay, so that's why they are stable. They are actually far apart from each other.
Okay, sir.
Okay, they are not like this. What I can say, they are not like this. Okay, then they will do steric repulsion, but the geometry will not be like this, right? Because these are all sp3 hybridized center, 109 degree, so they will arrange automatically like this. Chain system, linear system. Okay,
Yes, sir.
done?
Yes.
Clear, right? Fine. So suppose you have this, okay, here I am adding this hydrogen in presence of what? Rhodium alumina, Al2O3, okay, rhodium alumina, or what, or you have ruthenium. Okay, you can use any of this reagent as hydrogen in presence of rhodium alumina or ruthenium, or you can also use hydrogen, okay, in presence of what? Palladium carbon. Hydrogen in presence of palladium carbon. So what will happen? So if you use this reagent hydrogen palladium carbon in this compound, okay,
Trans products.
trans
Trans product.
trans product, how you will get? This double bond will not reduce. Why? Because this is aromatic system. This is aromatic compound. They will not reduce.
Okay.
Okay. Here addition of hydrogen will not take place like that. You cannot add the hydrogen here on this aromatic ring.
Yes,
Okay.
ester will convert it.
No, this is acid, na?
Okay,
So
okay.
here
That's
hydrogenolysis will take place. Okay, hydrogenolysis will take place. Hydrogenolysis means what? Bond cleavage. Okay, bond cleavage. Now you can see this is your benzylic carbon, right? PHCH2, right? This is your benzylic carbon. So this bond will break, and once the bond breaks, what you will get? This carbon oxygen bond will break. So you will get a compound like this. Okay, hydrogenolysis is taking place here. Okay, and if you use this compound hydrogen in presence of rhodium alumina mixture, okay, or you can use ruthenium metal also. So here you will get no hydrogenolysis. Okay, write down no hydrogenolysis. So what will happen here? In presence of this reagent, reduction of aromatic rings will happen. Okay, reduction will aromatic rings will happen. So one is your that Rennie-Nickel thing, and this is the second thing, rhodium alumina mixture, who can do reduction of aromatic rings. Okay, that rhodium alumina mixture can do, and this also can do, that Rennie-Nickel also can do. Okay, reduction of the whole aromatic ring. Fine.
Yes, sir.
yes, sir.
Done.
Done, sir.
Okay, so that is the end of our reducing agents. Okay, we are done with that, and next we have oxidizing agents. Oxidizing agents. So first of all, write down what do you mean by oxidation. So write down the first thing, that increase in what? Increase in oxidation state. Okay, these are just the basic definition. Increase in oxidation state. Okay, or I can say what? Loss of electron. Okay, loss of electron, or I can say loss of hydrogen. Okay, or I can say gain of oxygen. Okay, so these are the four things you have to know, or you can actually remember. Oxidation means what? Increase in oxidation state, loss of electron, loss of hydrogen, gain of oxygen. Okay,
Yes, sir.
done, right?
Yes, sir.
So the first oxidizing agent comes, that is our MCPBA. What is MCPBA? Metachloroparbenzoic acid, right? Metachloroparbenzoic acid. What is the structure of MCPBA? This is very important reagent. Okay, so meta position you have a chlorine. Okay, chloro par benzoic, so C double bond O, then you have oxygen, hydrogen. This is your meta chloro par benzoic acid. Okay. Now if you see here, basically in the peroxy bond you have two oxygen, right? So basically lone pair repulsion will be there, right? Now one thing is again there, see this oxygen is basically what? This is in conjugation with the carbonyl group, right? This oxygen is in conjugation with the carbonyl group, but this oxygen is not in conjugation, right? So what it will feel? It will feel what? Repulsion only. So keep in mind this oxygen atom that becomes what? Electrophilic. Okay, that is electrophilic in nature. I will show you the mechanism how it is becoming electrophilic, but write down electrophilic in nature. This has lone pair, but that is not of any use because this is not in conjugation. This oxygen is in conjugation, so that becomes electron rich, but this oxygen becomes electrophilic, so that means electron deficient. Okay, so electrophilic in nature, this oxygen, and therefore what? Therefore attacks on electron rich center, as it is your electron deficient, or I can say what? Electrophilic. So that means what? It will attack on what? Electron rich center. Okay, so it will show only your minus I effect, because this is not in conjugation, right? This oxygen is not in conjugation, so it will show only minus I effect, not plus M effect or plus R effect. Okay, so let me show you the mechanism. So suppose you have this, suppose you have a double bond here, okay, and here I am adding this MCPBA unit, so hydrogen, oxygen, then again you have oxygen, okay, and suppose you have this C double bond O R. So what I told, this oxygen is becoming electrophilic in nature. Okay, electrophilic means what? Electron deficient. So what will happen? This double bond, see, this double bond is basically electron rich center, okay, and this oxygen is electron deficient. So first of all, the double bond will attack here on this oxygen center. Now this oxygen has also lone pair, so that will attack on this carbon center. Okay, when it is attacking on this oxygen center, okay, this bond will break, okay, and as it is in conjugation, so this double bond will also break and it will abstract the proton from here. So that is the overall mechanism you have. First of all, this electron rich system is attacking on the electron deficient oxygen. As it is attacking on this electron deficient oxygen, this peroxy bond breaks. When it breaks, this double bond also breaks, because these are in conjugation, right? So when it breaks, this double bond also breaks, and if it breaks, it becomes O minus. So O minus will abstract the proton, which is acidic in nature. Okay, so ultimately what you are getting? You are getting what? Epoxide. Okay, and if I talk about what is the side product you are getting, see what is the side product you are getting. So this bond moves to here, so you will get here carbon double bond O. This double bond O is now taking up the proton, so it becomes OH, and what you have R. So you are getting carboxylic acid as your side product, and epoxide is forming here. Okay, epoxide is forming here. Is it clear?
Yes, sir.
Tell me if it's not clear, I will explain it again.
Yes.
Mechanism is clear or not? Epoxidation mechanism they ask in interview. Okay, people do mistake here in epoxidation mechanism also. It's a very simple mechanism, but they will ask what is the side product you will get, how you are getting the side product. Okay, so you have to show the whole mechanism and you have to explain it well. Clear?
Yes, sir.
Yes, sir.
Clear, right? Fine. So if it's clear, I am moving. So basically in epoxidation, what are the reagents we can use? So the reagents we can use, first of all we can use this MCPPA, that you already know. Okay, apart from MCPPA we can use DMDO, okay, dimethyl dioxyren, that is another reagent. Okay, apart from that we can use H2O2 in presence of NaOH, hydrogen peroxide in presence of NaOH. Okay, and last comes our Sharpless asymmetric epoxidation. So this here we have actually 4 epoxidation process, but each one is different from the other. Okay, each one is different from the other. We need specific conditions, then only you can do epoxidation. Suppose MCPPA is doing epoxidation, that is fine, but here what is the condition? That condition will be totally different when you will do Sharpless asymmetric epoxidation or when you will do H2O2 NaOH. So specific conditions required for specific reagents. Okay, all the reagents are not applicable to same kind of system or same kind of substrate. Clear?
Yes, sir.
First of all, we will discuss only about MCPPA, because today we will not able to discuss all the things. First of all, MCPPA we will discuss. So yeah, first thing is that, so if you have this kind of double bond and if you have MCPPA, so what will attack? Here also you will get scene attack or scene addition. So that means you will get a product like this. Okay, this is a 3-membered ring. Usually it's unstable, okay, but still it is forming. Okay, sometimes it becomes stable also. So whether you have cis alkene or suppose you have trans alkene also, suppose you have trans alkene and then you are using the same reagent MCPPA, so that time also it will take place by scene method. Okay, that time also scene addition will take place. So whether you have cis or whether you have trans alkene, it does not depend on the geometry, it will do its work. Okay, so it will do scene addition. Clear?
Yes, sir.
Okay, fine. So scene attack you have written. So if you are taking cis alkene, okay, so it will not change its stereochemistry cis to cis, and if you are starting from trans, so you will get trans product. Okay, you will get trans product. Okay, now I already mentioned this MCPPA is what? MCPPA is what? Electron rich or electron deficient? MCPPA
Electron deficient.
electron deficient, because the oxygen atom is electron deficient.
Deficient.
Okay, so which kind of substrate we need?
Electron rich, sir.
Electron rich. Just a minute. So write down one line that more electron rich bond is attacked. Okay, more electron rich bond is attacked. Okay, so suppose I have this molecule, suppose I have this molecule. Okay, here I am using MCPBA. Okay, 1 equivalent, DCM is the solvent. What will be the product?
Sin attacks is in addition.
In addition, which double bond it will attack?
First, sir, the one which is connected to 2 methyl.
So
The one called
this double bond is basically what? This is electron rich, right? This is more electron rich because you have 2 methyl groups. You have plus I effect as well as plus H effect. Okay, plus I as well as plus H, hyperconjugation and inductive. So definitely what will happen? Epoxidation will take place, and definitely syn addition. Okay, syn addition. So suppose you are forming the epoxide ring. This is epoxide ring. So epoxide ring you are forming above the plane. So that means automatically the methyl will move to what? Methyl will move to below the plane. Okay, automatically they will move to below the plane. Okay, syn addition is also taking place, and remember electron rich. Okay, electron rich double bond will be attacked. Clear?
Yes, sir.
Clear. Kaveri, clear?
Clear, sir.
Okay, Sampriti, clear? Sampriti,
Yes, sir.
clear, right? Okay, that will be revision for you. So this, suppose you have this. Here also I am using what? MCPBA. MCPBA, DCM is the solvent. So what will be the product? What will be the product here? Epoxidation will take place, na? But what will be the plane of attack? Above the plane or below the plane?
Above the.
Why above the?
Because below the plane there is.
Below the plane you have already this OCH3 group. So the
Yes, sir.
epoxidation will take place from above the plane. Okay. So this is what? This is your steric factor. Okay, steric factor. OCH3 is below the plane, that's why the epoxidation is taking place from above the plane. Okay. Okay, good. Now suppose you have this. Here what will happen?
So here sin addition happens, but below the.
So if you do here below the plane, that will be wrong. Okay, that will be wrong. Now what is the reason here? So if you have OH is what? It's a polar bond, na? This hydrogen is acidic, right? This OH bond is polar. Okay, and if you have this what? MCPBA reagent, okay, so that electrophilic oxygen, whatever the electrophilic oxygen you have, so if I am drawing here OH, and here you have this thing. Okay, so this electrophilic oxygen will do hydrogen bonding. Okay, if you have OH functional group, or if you have any kind of acidic proton, okay, acidic proton, what is the condition for hydrogen bonding? You need one electropositive and electronegative element. That's it, right? So here this proton, this H proton from your OH functional group and this oxygen from your MCPBA reagent, okay, they will do hydrogen bonding. Okay, when they are doing hydrogen bonding, okay, so that time what will happen? That time the epoxidation will happen from which phase? If it is doing hydrogen bonding with the OH, so OH is already present in above the plane, so that means the epoxidation will also take place from above the plane. Clear? If OH is present in above the plane, the epoxidation will happen from the same phase because due to hydrogen bonding. So here what is the reason? Hydrogen bonding. Clear? Clear or not?
Clear, sir.
If you have only OH, then
Clear,
only it
sir.
will happen. Okay. It is not OCH3. Why in case of OCH3 why hydrogen bonding is not possible? Because here you do not have any acidic proton, right? Fine. Now suppose you have this. So initially you have this OH, and here I am taking this TBDMSCl. Okay, tertiary butyl dimethyl silyl chloride. Okay, tertiary butyl dimethyl silyl chloride. This is actually a protecting group. Okay, this one is actually a protecting group. What is the reagent? So the reagent looks like this. You have this, okay. Again, don't think SN2 reaction will happen here. Oxygen will donate the lone pairs in the vacant d orbital of silicon. Okay, and I already told you that silicon oxygen bond is very strong bond. Silicon oxygen and silicon fluorine, these are the two strong bonds you have to consider in organic chemistry. And don't think that OH will attack here, chlorine will leave, SN2 reaction. It is not an SN2 reaction. Oxygen will donate the electrons in the vacant d orbital of silicon. Okay, so oxygen is donating the electrons here, and what will happen? Chlorine will leave. Okay, chlorine will leave. So ultimately what we will get? We will get O. Then I am not writing like this, I am writing here simply TBDMS, tertiary butyl dimethyl silyl. Okay, O TBDMS. Okay, so this is a protecting group. Protecting group of what? Protecting group of alcohols. Okay, now the alcohol is protected here. Okay, and now if I give here MCPBA, okay, MCPBA in presence of CH2Cl2. CH2Cl2 means what?
Carbon, sir.
Carbon. What is the name?
Dichloromethane.
Dichloromethane, DCM, right?
Yes, sir.
CH2Cl2 means your same thing. DCM is the solvent. Fine. So here the epoxidation will take from which phase? Here the epoxidation will take place from which phase? Below, because you do not have any acidic proton. And OTBDMS, this is a bulky group. Okay, so the epoxidation will take place from below the plane. Clear? Clear?
Yes, sir.
Done?
Done, sir.
Done, right?
Yes, sir.
Okay. Suppose you have this, 2, 3. You have this, and now I am using this MCPBA. So what will be the product? Tell me quickly. What will be the product here?
In addition, but it will attack from above the plane.
So here you have OH, right? If you have OH, that time the epoxide will happen from above the plane. Due to what? Due to hydrogen bonding. So that you have to check, and you have to be very careful in exam what they are giving. They are giving OH or other oxygen containing groups. Okay, If bulky group is there, that time steric factor will take place. If OH is there, that time hydrogen bonding will take place. Fine. Done. Suppose you have this, here you are using NBS, okay, and second reagent you are using NaOH. So if you don't know NBS, NBS is basically what? N-bromosuccinamide, okay, and if you have N-bromosuccinamide, so that is basically source of what? Source of Br plus, okay, this bromine electrophile. So basically you can think like that, you have a double bond and you are using bromine molecule. I think in class 12 you have read this double bond, and if you have bromine, what will happen? Cyclic bromonium complex is producing, right? This kind of cyclic bromonium complex is producing there, okay. If you want to show the mechanism, so same type of mechanism. The double bond will attack on the bromine, okay. One bromine will be delta minus, one bromine will be delta plus, okay. Now bromine will attack through the lone pair, and this bromine is leaving, okay. When it attacks on this bromine is already leaving, and now this bromine is attacking from the lone pair, so you are getting this kind of cyclic bromonium complex plus Br minus. So same thing will happen here also. If you are using NBS, so that is the source of Br plus, okay. They are not giving simply bromine, otherwise you can do it easily, so that's why they are writing this NBS, okay. So already this is above the plane, so if you have above the plane, the bromonium or bromination will take place from which plane? Below the plane, due to steric factor, okay. So bromine is getting positively charged here. Next step, you have NaOH. So when you have this kind of thing, so you have NaOH. Now the question is, so you have Na plus or OH minus, fine. So now the OH minus is not here base, here it will act as a nucleophile because you do not have any kind of acidic proton, right? So now the question is, OH minus will attack in which position? This position or this position? That is the question, okay. So for that, first of all you have to draw this cyclic this cyclohexane in what? In your chair form, okay. First of all draw it in chair form, okay. Now see, where you have the OCH3 group, OCH3 group is above the plane, so if above the plane, don't put in axial position, otherwise 1,3 diaxial interaction is there, so try to put in the equatorial position, okay. Whatever above the plane you have, that try to place in the equatorial position, not in the axial position, okay. So if you put here OCH3, next carbon you have this 3-membered ring, and that is below the plane, so that means like this, okay. So that is the compound you have. Now OH minus is there, so now the question is, OH minus will attack which position? This carbon or this carbon? What do you think? Am I audible?
Yes, sir.
Where it will attack? This carbon or this carbon? 1, 2.
First carbon, sir.
Why first carbon?
Because
Second one.
Why second one? I already mentioned it. Mode of attack of nucleophile. Always it will attack from your axial position, right?
yes, sir.
Axial position. Now see, if OH minus attacking from this here, so which side it is attacking? It is attacking from axial position. Check.
Actually,
How can you check? So see, after attack what you are getting? OH is present here, okay, and bromine will go there, okay. So that is axial attack, okay. If OH minus is attacking on your number 2 position, that time what you will get? First of all, that is not possible because this center is not free. See, here this ring is there, but this center is free, it can approach from here easily, okay. This center is not that much free, you have to approach from this side, okay. and if you also approach from this side also, okay, then only you have a possibility. Suppose OH minus is approaching from this side, fine, so your bond is breaking, fine. So whatever you will get, check what you are getting. So now the incoming nucleophile is coming in the equatorial position, not in the axial position, okay, and that bromine will go also to equatorial position, okay. So keep in mind, when the nucleophile is attacking, or nucleophile have to choice between like which position it has to attack, so always from axial position it will attack, okay, that you have to keep in mind, axial attack. Axial attack will take place, okay. In the first class of carbonyl chemistry, I have given some example, na, that cylindrical type acetylide CH3 minus, okay, remember that class, you will get to know, okay, or check your notes, you have that, okay. So whatever the nucleophile you have, the nucleophile will approach from the axial side if it is not that much bulky, and if it is not do that kind of 1,3 diaxial interaction. If 1,3 diaxial interaction or steric hindrance is there, that time equatorial attack is possible, but most of the cases, if it is not, OH minus is not that much bulky, so it will attack from your axial side, clear. So that will be your major product. Kaveri, clear?
Yes, sir.
Clear, right? Fine. So that's it. Okay, that's it for today. Hooke's model we will start tomorrow, not tomorrow, in the next class, okay. Before ending, so tomorrow we will start organometallic chemistry, okay. Tomorrow we will start our inorganic chemistry, which is your organometallic chemistry, and after that we are done, okay.